Wind drives a lot of how the ocean functions. Waves, currents, and the global circulation of water all rely on the important interactions between winds and our planet's systems. Over time, atmospheric CO2 levels have risen and fallen many times, creating what are known as glacial and interglacial periods. However, CO2 in the atmosphere has been rising 100 times faster in the past 60 years than naturally expected. Upwelling, which is driven by wind, plays an important role in the physical carbon pump. It pulls nutrient and CO2-rich waters from the deep ocean currents to the surface, where a gas exchange occurs and the CO2 is able to enter the atmosphere. Until now, there has not been enough direct evidence for the interconnectedness of wind, upwelling in the oceans, and atmospheric CO2, as well as its impact on changes in the Southern Ocean. To assess what might have caused these changes and a deglacial rise in CO2, scientists have used biogenic opal collected from 3 cores from the most recent deglaciation and 1 from the last glacial period as an upwelling proxy. These cores are useful because they have a high accumulation rate and are therefore useful for showing what past conditions of the ocean looked like. The production and burial of biogenic opal in the Antarctic Polar front, where the cores came from, is linked to upwelling. This is because the diatoms feed off upwelled nutrients, and when they die, their outer shells fall to the bottom of the ocean to create the biogenic opal. Where there is lots of upwelling, there are lots of diatoms, and therefore lots of buried opal. And from the higher rates of opal accumulation, as a result of increased dissolved silica levels during deglaciation, it can be concluded that enhanced upwelling in the Southern Ocean occurred during this time. From these cores, we can see that upwelling was at a maximum during deglaciation. As upwelling increases, it changes the chemical signatures of global circulations, such as the AAIW, SAMW, and both the southern and northern hemisphere westerlies. These signatures then travel through the thermocline and then up to the surface waters around the globe. This is evident in the north-south hemisphere linkage, whereby as one has a period of warming, the other has one of cooling as an eventual result of upwelling. The opal fluxes in the cores showed that increased upwelling coincided with deglacial warming in Antarctica, a rise in atmospheric CO2, a changing signature of deep North Atlantic waters to resemble that of Antarctic waters, and a southward shift of southern hemisphere westerlies. The combination of these effectively induces a reorganization of global atmospheric circulations. This correspondence shows that these systematic changes were influenced by wind as the primary driver, as well as increased heat fluxes in the ocean due to rising air temperatures and the downward mixing of surface water. This correspondence is now being impacted by anthropogenic activity and could soon be altered in a previously unprecedented way.